All right, welcome to the last day of the conference, where we are going to discuss the next 10, 20, 100 years. And we'll start with Anne Bizouard from the Observatoire du Côte d'Azur.
Absolutely. In France.
In France.
In Nice.
Take it away.
Let's start. Okay.
Let's start.
Thanks for giving me the opportunity to tell you what's going to happen. Actually, I will concentrate my presentation more on the detector part and what we are doing in LIGO Virgo CaGRA collaboration in terms of detecting core collapse supernova. So this is a list of things to detect supernova. You need, this is a cooking, this is not the right version. Okay, this is weird. Okay, okay, fine. So you need the sensitive detectors. You need also multi-messenger information, as we already discussed. So I will mention briefly those aspects, and you need also models to be able to develop the pipelines to make detection and do the physics we want to do. So I will briefly, so as I was mentioning, I will mainly address the detector part and the developments in the algorithms part today. So let's start with the detectors. So this is a current list of detectors that are used on Earth right now to do gravitational wave physics, the two LIGO detectors. In the USA, Virgo in Europe, and we have CaGRA in Japan. So, and those detectors are currently actually taking data. And this is an example of the sensitivity of so here you have the sensitivity curves of the two LIGOs in blue and red as function of the frequency, and in magenta you have Virgo. So you see the difference between the sensitivity of the detectors. So to quantify the sensitivity, we usually use the binary neutron star range, which is the average distance at which we detect a source with SNR of 8. And the difference between the two LIGOs and Virgo is typically a factor of 3. LIGOs right now, they have their range is around 160 megaparsec, while Virgo is stuck at 50 megaparsec. And CaGRA currently is not acquiring data for observing for observation, but they are back to commissioning to improve their sensitivity, because they are at 10 megaparsec right now. So what's important is to have a good sensitivity curve, but you see it's quite messy. The sensitivity curve is not the one you usually see with a smooth curve. It's actually more complicated, and I will mention that the data are not, we're already mentioning the data are full of glitches. They are full of lines, spectral lines that are also annoying for detecting signal. And another important ingredient in those detectors is the duty cycle. I mean, we are trying to have to make them taking data permanently, but from time to time we lose the control of the detectors and we don't have data. So when you look at, for instance, the duty cycle in triple or double coincidence mode, you see that it's only around 30 or 40% of the time. So it's not 100% of the time we have coincident data. Let's move on. So this is a schedule of the different runs. As I was mentioning, so we are right now taking data. We are at the end of the 04 observing run. Very soon we will end, and there will be a period of upgrade before the next one called 05 that will start hopefully end of 2027 or a bit later. I will mention that. So this is a run where the sensitivity is, we expect a gap again from 160 megaparsec up to more than 200 megaparsec for LIGO. And for Virgo, it's not yet totally clear, and CaGRA is expecting more than 100 megaparsec in terms of sensitivity. So the upgrade, so things that will happen in the next years with the detectors, so the preparation of the 05 upgrade. So of course it's already prepared. So for LIGO, it's a quite light upgrade that's supposed to last only 2 years, and the goal is to increase the laser, but not only to increase the laser. We know how to build a high power laser. The point is to be able to control the cavities and to make sure that the amount of power inside the cavities is not making your life difficult to control the cavities. So that means to work on reducing noise, reducing have better coatings on the mirrors to avoid thermal effect. When you have a lot of power in the cavities, you have thermal deformation. It heats, even if the coatings, even if the mirrors are very, very nicely designed and manufactured, you always have defect, and any default on your surface can be an issue, because it will generate a deformation of the surface of the mirror, and you lose the control of the cavities. So it's really an issue to increase. Very difficult, actually, to increase the power inside the cavities. So they will also change the beam splitter, and they will apply the new coating recipe to reduce thermal noise. So Virgo upgrades is more it's more complicated. It will last longer. The point is that what we realized in 04 is that our recycling cavities, because we install the signal cavities, and trying to control the detectors have been more difficult than foreseen, because our recycling cavities are unstable by design. So we struggle to, and this is why our current sensitivity is lower than expected. And so we have decided to change the design of the cavity, of the recycling cavity. So that means we need to change a suspension. We need to add suspension, so it's more invasive than the LIGO upgrades. That's why it's going to last a bit longer. So the plan is to be able to join 05 at the very end. Actually, things are not completely decided, because you will see things are a bit more complicated recently with politics. And for CAGRA, so the point is, again, what I forgot to mention is CAGRA is underground, and with the test masses are cryogenic. So it's more complicated than LIGO and Virgo design. And they are struggling with many problems they discover with that. So their goal is their goal for 05 is to reach more than 100 megaparsec. Yes, so yeah, talking about 05, when we say 05, we will reach 240 megaparsecs of sensitivity. Actually, it's not going to be 240 megaparsecs the first day. Well, the current plan is to go by stages, with meaning there will be so a 2 years upgrade. Then we take data, then we break, we make commissioning, we improve the sensitivity. But the final goal is to reach to improve the sensitivity by different stages. That's why what is proposed right now is to have, like in 04, we had 3 stages, 04A, 04B, 04C. For 05, that will be something similar, meaning it's going to be a several years run, but break by period. So things here, I mean, what's written here is just plan. It's not really well settled right now, because actually there's another thing that happened recently is so those upgrades needs to be funded. And as you may know, so in the US, the Trump administration budget foreseen a cut for next year. So the upgrade, which was supposed to start beginning of 2026, might be delayed because of this uncertainty, because right now the project, it's a cut of 50%, which is huge, meaning that would mean a delay of the upgrade. It's not yet voted. It's going to be decided in October. But voilà, there are some uncertainties. And on the Virgo side, what we learned in June is that we are not getting the money for 26 as well for our upgrade. It's going to be delayed and maybe spread over more years than foreseen. We were expecting to be able to do the upgrade over 4 or 5 years. It might be longer, actually. So that's not the good news of the day, but there are some uncertainties. The point is really to make those upgrades because we need to improve the sensitivity when the planning is uncertain. So I was talking about 05, the upgrades for 05, but then we are already thinking to after 05. So it's called post 05 upgrade. So and the point. There are plans both for LIGO, for Virgo. So in LIGO, it's called A#, Virgo, it's Virgo Next, and Cagra, it's Cagra Plus. And the point is, again, to continue to push the limit of the technology, meaning increasing the power. As I was already mentioning, it's not that easy to control the cavities with high power inside. So to reduce the thermal noise, that means one solution is to have bigger test masses by just changing from our current mirrors that are 30 kilograms to 100 kilograms. We can reduce the thermal noise, which is a noise actually in this region. By increasing the laser power, I forgot to mention, you increase actually the sensitivity in the high frequency region. And the low frequency region is dominated by seismic noise, control noise. Here you need to work on your control system and suspension to improve the situation at low frequency. But there's another thing as well, which I did not mention in terms of improvement of sensitivity without increasing the laser power at high frequency is the squeezing. By squeezing the light, we can actually improve the sensitivity at high frequency. And now we are able also to control, to also squeeze the light in the low frequency regime. So squeezing is something which has been, which is already used in LIGO and Virgo and Cagra, and this is something which is very, useful because you don't need, in that case, you gain the same sensitivity by not increasing the laser power. As I was mentioning, increasing the power is not that easy. So post 05. So I was mentioning there's a program with lots of possible upgrades. And in terms of sensitivity, compared to the current sensitivity that you have here, or here you have 04. But so 05 is going to be this curve, the brown curve. And the upgrade after 05 is this a blue curve. Typically, you will gain a factor 5. So actually, those upgrades are the intermediate step within the current infrastructure, I mean, on LIGO, Virgo, and Cagra, but to prepare the third generation detectors I will mention. Because this is, again, we gain, so we go by step because it's not that easy. So before talking about the third generation detectors, I want to mention that there are IDs of other detectors on Earth. And actually, there is one, it's not an ID, but there is one which is under construction. It's a LIGO detector in India. So I did not mention that. It's under construction. It gets a little bit delayed, but it's the same technology. Actually, it's a LIGO detector. It's a former first generation detector that was inside, that was installed at Hanford, that is moved to India. And there is another project, which at least a project, something put in that is proposed. It's a project of detector in Australia. So initially they were proposing to do some to focus on the high frequency to build a high frequency detector to drop the low frequency, which is complicated because of the seismic noise. But Jade, talking with Jade, she was telling me that actually the Australians are thinking about another design. There's possibility. So maybe in the future, maybe it's just idea for the moment, we will have another detector in the south hemisphere, and that would be very great for improving our coverage of the sky. So let's move to third generation detectors. So right now there are two projects. One in Europe is called Einstein Telescope, and one in US called Cosmic Explorer. So Einstein Telescope is an interesting project because it was proposed in the initial proposal more than 15 years ago was to have a triangular design. And actually, it's not one single detector. It's equivalent to 3 detectors in the same place. And the reason of this design proposal was to get the polarization. We were discussing that yesterday. If you want to get the polarization, to be able to measure the polarization, you need to have non-aligned detectors. So one solution is with a triangular design, you can measure at the same time the two polarization. And so the Cosmic Explorer, so the design proposal for Einstein Telescope was a 10 kilometers arm long, underground and cryogenic. I was mentioning CAGRA has lots of difficulties. CAGRA is already underground and cryogenic, and they are facing lots of difficulties. That's good to have people already challenging your proposal in some sense. So I will mention that actually people in Einstein Telescope are thinking maybe of changing the design right now. So Cosmic Explorer is different. They use, they take typically LIGO design, optical design, L shape, and they make it longer. So meaning same technology on Earth at room temperature, but with arms 10 times longer, 40 kilometers. And actually what they are proposing is to have 2 detectors, one with 40 kilometers arm and the other one with 20 kilometers. The problem is the cost. Because the vacuum chamber is something that costs a lot. So in terms of sensitivity, you have the projected sensitivity for those detectors. Here you have H-sharp. So this is a post-05 sensitivity. This is 05 sensitivity. Here we are here. So you see the gain between the sensitivity of current detector and what is projected for those third generation detectors. And the point is to gain everywhere in frequency. At low frequency, especially Einstein Telescope, you go underground so you can beat the seismic noise. At high frequency with more power inside the cavities. And here in the bucket where you're dominated by thermal noise, you need to have bigger masses and very good coatings and material. So in any cases, it's about beating the limits of what we know to build right now. So it's very challenging. In terms of physics, it's, the physics that will be possible with those 3G detectors is huge. And we won't be, I would say, background dominated. We'll be limited by the fact that signal will overlap in those detectors. So the next problem in those detectors will be to how to deal with signals that overlaps. Something that the LISA community is already I would say facing, because in their case they have many nearby signals that will overlap in their data. But for Einstein Telescope and Cosmic Explorer, that will be the case. So the physics program in terms of astrophysical sources and fundamental physics and cosmology is huge. I'm not going to mention that because we are dealing with core collapse supernova physics here. But the point is to be able to develop the technology. It's not going to be trivial. And that's why those upgrades, the upgrades of the current detectors are very important, because we are not going to build third generation detectors out of the blue. We really need to, I don't like to say that, but to use the current detectors as prototype, or at least the arguments to do R&D to develop and to really develop the breakthrough technology that will be able to, that we need for Einstein and Cosmic Explorer. Timeline, so both are at the conceptual design stage. And I was mentioning technical challenging and the cost. Of course, they will cost a lot. It's at the level of several billions each detector. So it's not something that is that you fund easily. 2 words about Einstein Telescope design. I was telling you, so the initial design is triangular, and I was mentioning 3 detectors. Actually, it's not 3 detectors. It's 6 detectors, 6 interferometers. It's something you need to realize, the complexity of the design, because it's a high. When I was mentioning Einstein Telescope is going to be good at low frequency, it's because actually we will double the interferometer. There will be one running cryogenic, running, so where the test masses will be running at 20K for the low frequency. And to get the high frequency sensitivity, there will be another interferometer in parallel to each of the 3 detectors with high power, so running at room temperature, but with lots of power inside the cavities. And the point will be to be able to recombine both data stream and so on. I have no idea how it's going to work, because when we present, the sensitivity curve of Einstein Telescope showing low frequency and high frequency, actually we combine both. But in the design, it's very complex. Six interferometers sharing, so underground, sharing in the same tunnel. You see the number, typically the number of vacuum chamber you will have, it's huge. And now there's another thing people are realizing is that because the detectors are in the same tunnel, they are nearby, there will be correlated noise. That means the 3 detectors we are talking about to be able to measure the polarization, actually it's going to be more complicated, because they will see they will be correlated noise. And correlated noise is really difficult, because all the methodology we are considering to extract the signal, usually we use coincidence and we use coherence. So we always assume there is no correlation between the detectors. It's not going to be the case anymore if you have collocated detector. And this is something LIGO, first generation LIGO detectors learn. So we are, in some sense, rediscovering something well, anyway. So what's happening in Einstein Telescope right now is to think about, maybe we should have L-shaped detectors separated. So 2 in Europe somewhere, for instance. So there's been a study last year where, and this is the document if you're interested, to understand, what will be in terms of physics, what will be the best strategy. Should we continue to have this very complex design with 6 interferometers, or should we go to a design closer to what Cosmic Explorer is proposing, 2 L-shaped detectors on Earth? Oh, no, underground, actually. Okay, so timeline. There's no precise timeline, I can tell you, because it's no. So but just to give you an idea, I mean, we're supposed to discuss today 10 years. I mean, the next 10 years, not the next 20 or 30 years, because 3G, yes. I don't know if I will see Einstein telescope during my life, but 05, yes. A sharp, yes. So meaning this is a 10 years landscape. So now I move to data analysis. So first thing about core collapse supernova is how many sources we expect. So in the Einstein science book that has been published this year, there's been a nice study, a nice work done by I think Marco and others, about trying to get all the information of what we know in terms of observation, models, and theory about how many sources we're going to observe in our nearby universe. So 10 megaparsec is more than nearby for supernova physics. And if you consider 10 megaparsec, if you consider all models, it's typically what you obtain is 1 per year. But we know that it's 10 megaparsec is not reachable even with 3G detectors. So I'm going to skip that. There's been what I wanted to mention is a number for our galaxy. It's still around 1 or 1 per or 3 per century, whatever number. It's not changing. I mean, the panorama will remain the same. Then, in the remaining time, I will address few ideas for what we should do to be able to detect a supernova, I mean, the next supernova. And what we know, that they are rare and faint. That will remain true. We know that they should be accompanied by neutrinos or antineutrinos, and from time, not always, but with electromagnetic emission. Because the two multi-messenger, the two other messenger, neutrino and photons, are not guaranteed, we will continue to have these two approaches. One based on the fact that where we consider we search in our data a signal coming at any time, anywhere, meaning we don't have any information, any other information that tells us that there's a supernova that happens. So this is a all sky, all time search. And then we continue to do targeted search where we have an electromagnetic signal and a neutrino signal. So targeted search is what we are doing with the optical supernova observation. But when we have the most interesting thing is to have the neutrino information, and I will mention that. So first, all sky, all time search. So what the pipelines you already heard about yesterday, and Sergey will also present some new ideas of how to improve our searches. But what they basically do, those pipelines, is to search for an excess of energy in time frequency. And so I'm a bit provocating saying it's a clustering problem, because the point is to be able to get all the energy of the signal without getting the noise. So it's really a problem of finding the signal in time frequency. The usual assumption that all the algorithms are doing is that the signal is localized in frequency and time, which is, when you look at this picture, it's not really true. I mean, you clearly see that the signals are separated. So most of the times we are able to detect one part of the signal, the strongest, but we miss part of the signal. So that's going to be a challenge in the next year, is to be able to reconstruct better the signal. Yeah, I want to show this plot because that shows the problem we have with this approach, agnostic approach, where we don't make a lot of assumption on the signal. Here it shows for different models the injected SNR. I mean, on the x-axis you have so it's simulation in some noise. This is injected SNR, and if you take the black point, it's the detection efficiency of 50%. On average, it's average over different sky position and so on. But what you see is typically to get 50% of detection efficiency, you need something like a SNR of 20. It's match filter SNR. That means that if you compare to what compact binary coalescence search are doing, they are able to detect with SNR well over, typically 6. That means when we search for collapse supernova, we are quite inefficient. We are losing half of the signal, and we really need to improve that. And I think Sergey will mention in this talk how to bridge a gap, because here there is typically room for improvement. If we gain a factor 2, that means we gain a factor 2 in distance, we gain a factor 10 in number of sources, but there is a problem of number of sources we have in a nearby galaxy. But anyway, there is room for improvement. So I was mentioning that. There's another way to improve also the way we do this kind of agnostic searches is to fight against the glitches. And we already discussed that yesterday. And I have a good hope that machine learning methods will help a lot, because we can train with machine learning, we can train on the algorithm to be able to recognize what a glitch is and what a signal is. Reduce the frequency band. Christine mentions that. It's another idea to fight against the background. And another important thing is that we need to be able to analyze any stretch of data. Right now, when we have only a mention at the beginning, when coincident interferometer duty cycle is not, I mean, it's between 40 and around 40%. That means that we are losing some. I think the single I4 duty cycle is around 20%. We are losing some data where we could have an event one day. So we need to be prepared to that. It's tough because you're dominated by the background because you can't do any coincidence, but it's important. Here, the fact, I mean, I mentioned having models and robust prediction with model would I think help developing those methods. So now let's move to targeted search. So here we're dealing with the multi-messy aspect. Anyway, using another messenger, electromagnetic neutrinos. I was mentioning electromagnetic. You understood that it helps. It reduces the amount of data we are looking for a signal, but typically 5 days, it's too much. We don't gain a lot. We gain, but not that much. Neutrino would be the definite. It's a dream to get, because in a neutrino signal, if we have the neutrino signal, we know the 1 second of data where we need to look for. And in that case, for me, it's no more a detection problem. It's a parameter estimation problem. I mean, we directly dig into. I mean, we know where to look for, and we will try to reconstruct everything from the signal. So here, this is very clear that to do parameter estimation or source properties analysis, we need models to get all the components, expected components. And I'm very happy. There have been quite a bit of talks addressing this problem. Then future ideas for the next year. That's been mentioned. Template search. Should we go in that direction? Actually, it already exists. That's been already developed for the bounds, because here it's easy to modelize the bounds. So you can have template bank with simplified model, but actually simplified models that you can test with waveforms. Actually, waveforms that because now there are some bank catalogs of waveforms for the bounds. So I think there will be lots of developments trying to be able to build a template bank for simplified model at the origin, but with machine learning techniques, I think we will be able at some point to, it's a dream to have a generator for waveforms, including any feature. Any feature, I don't believe that, but at least the most robust feature, the bounce, and maybe the proton-neutron star modes, why not? I would guess that should happen one day. And then the joint, another thing we should, which is interesting to think about, is how to use neutrino and gravitational wave signal together. That's been mentioned for SASE, for instance, because we expect something correlated. So that being able to join two information in the likelihood would increase, of course, the significance of the event and would give more, first of all, would provide information about the physics, but also give weight to the detection. So that I already mentioned the source properties. When we have one event, the one event we are all dreaming of, it's clear that we will try to extract all the feature we see in the data. So there will be lots of activity. Extract the feature with gravitational wave, including neutrino information. Classification, is it a neutrino-driven explosion? Do we see anything that would be related to MHD mechanism and so on? I think this is very important. Measure the rotation if we see any hint of rotation and so on. And Marek mentioned what the kind of information we are currently giving in our alerts, because if we see a supernova, actually tomorrow we will send an alert if it's significant. But right now we are giving very, I would say, simple information like the peak frequency, the duration, and what else, and the significance. Hopefully, if we are able to develop those algorithms to extract more information, we should provide that in the alert as well. It's a dream for future. But for that, we need to have. Such kind of developments will rely on models. It's obvious. Okay, so I think I wanted to mention the problem, because I've been questioned yesterday about the quality of the data, the glitch. Just to give you an illustration. So this is what we call a glitchogram that shows here as function of time. Here you have, it's in Livingstone over 24 hours. The points represent a glitch, and the color represent actually the strength of the glitch in terms of SNR. So the red are the most annoying. It's SNR 20 glitch, and that the one where we could have that usually are annoying for the analysis. So you see the rate of those events for 24 hours. And this is a very quiet day. That was 2 days ago. Usually in summer, the detectors are quieter than in winter. This is in last December. You see the rate of those annoying glitches increasing a lot. So that's a reality of our searches. We are not background free. So we have to deal with that. So it's a confusion. If we have only, we were discussing that yesterday, if we have only the bounce that looks like a glitch, it's going to be difficult and require a little bit of work before saying for sure this is a real signal. And that's so yeah. And this is my last slide about future direction. As usual, two ways. I mean, we need to work on the detectors. We need to have more sensitive, more reliable detectors, increasing the duty cycle. And we need to work also on the algorithms to improve our sensitivity. I think we can play both ways, and this is what we are going to do. And the last thing I want to mention, because I don't know if everyone knows, the LVK MOU, I mean, that defines the LVK collaboration, ends at the end of 2004. That means next year. And it's not going to be renewed. So one thing we know. And what has been proposed actually is to replace the LVK by something that's called IGWN, International Gravitational Network. So it's a new consortium. So most of the LVK will move to IGWN, but it's open also to other groups. I don't know exactly, if, I'm not really too much involved in that, but just to warn you, the LVK will not exist anymore in 1 year, actually. Okay, I'm done.
Thank you. Now that I see a lot of depressed faces in the audience, okay, I don't know who was first.
Gravitational waves from supernovae are very broadband. So if ET is split into a low frequency and a high frequency interferometer, could that potentially cause problems for us if we have half of the signal in one and half of the signals in the other one?
You see that we are always presenting one single sensitivity curve. I have no idea how, h of t will be reconstructed. But I suppose we always assume that we have the low frequency and high frequency in one h of t channel. I don't know how. I don't know if people know how to do that. No idea.
Okay, to depress the audience even more, I just have a comment. Like 6 detectors in one vacuum
One tunnel.
pipe,
Right.
it's impossible. We should remember that LIGO
Right.
was qualified to run 2 detectors in a single one, so they outsourced it to India.
It's not the same vacuum chamber. It's different vacuum chamber, but in the same tunnel, you will have 4 actually, because you have, you have you have 2 and you double with low and high frequency. So you will have 4 vacuum chamber in the same tunnel. But it's super complicated design.
Quite worried about that man on your picture if he was in the vacuum.
Yeah, thank you for the great talk. I think there will be a lot of questions that you will generate tonight. So the one question actually is made in 2 parts, is involving the 3rd generation, in particular the 2 configuration for Einstein telescope. I know whenever a collaboration tries to do new technology, the mass of experimentalists that are actually working on it is a critical factor. We know that probably for Kagra, the mass was a little bit too small to make things successful, but for LIGO was probably enough because they made it work. So my impression is that the amount of experimentalists that are going to be behind Cosmic Explorer is going to be such that they might be able to develop new technology in a stable way. But related to that, is there any specialized effort to understand for specifically Scorchola supernovae, which of the 2 configurations are better?
Alors, there's been some, you mean the triangle on 2L? No, actually, I have a slide that shows that. Actually, there's basically no difference. So, it does not really, no. I would say it's not core collapse supernova physics that will tell which configuration is the best. I mean, the point is that between the triangular and the 2L shape, the main ingredients that we should remember is that the triangular, it's 10-kilometer arms. The 2L are 15 kilometers armed. And it's the length that makes a big difference because it decreases sensitivity. So it's not really, I mean, in terms of location or blah, 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 does not really matter. What is really important is the length of the arms. And you're comparing 10 kilometers over 15 kilometers, so it's.
Do you know what the answer is compared to string length?
No, actually no, but you're risky.
No, but the lines are quite similar.
Why?
The 10-kilometer angle, 2L for 15 kilometers. I wonder how bad it could get if the 2Ls are also 10 kilometers.
But it's going to be. No, I mean, if you decrease it, it's really the length is doing a lot here.
Now the 2L is 15 kilometers, right?
15, yes.
Yeah. So if you put that at the same.
But meaning. You know, it's SNR here. Sorry, because I was thinking in terms of distance.
Right. In the interest of time, let's keep questions and answers.
Well,
brief.
we can
Yes.
discuss, but
Okay.
Thanks for the nice talk. I have a follow-up question. In the design study that you showed, there are also 2L shape with 10 kilometers and 2L shape with 20 kilometers. So I was wondering why you prefer the 15 kilometers. Is there a preference for that design?
Honestly, I don't know the answer. I should check, but right.
Yes. Right.
Thank you. Thank you for the talk. So this question is more aligned to various group people's. So I'm working on both anomaly and template-based machine learning as core collab search pipelines, and we have very mature review system for anomaly searches, online search pipelines. But however, if like template-based pipelines, do we have a review system for it? And if there is a review system, what should be the criteria for template-based core collab searches?
To my knowledge, there is no review template-based match filter pipeline. You know, no, because you know it's really I think it's not mature yet. I mean, to really reach a step where you get reviewed and you really say you're going to apply it to the data and so on. No. Once it's more for parameter estimation, I think it's a bit more developed in the targeting parameter estimation when you have one event trying to get the bounds and you know more than that.
I just make a quick comment. I think this is not possible for knowledge. It's an infinite parameter space.
Right.
Each simulation takes months. It's impossible to have a template search, and we don't even can predict, you know, how the waveform depends on the initial parameters.
No, we simplify, but you don't
It's
get
kind of a
simplify model.
fantasy to have.
Right.
I don't know, maybe I'm wrong, but
Yeah, it's.
I'm going to get the microphone. No. Okay, Christine, go ahead.
Thank you very much for the nice talk. So I have a question about, because you mentioned that Einstein telescope started with that triangle configuration because we want to measure polarization. So now if we were to switch to that L-shape configuration, is Einstein telescope communicating with the Cosmic Explorer to find the best orientation, to their telescope so that we can still achieve that polarization?
Well, the point, no, it's a good question. And this is what we should do. Fortunately, think about what is the best localization for the different interferometers for the global network. Fortunately, choice of sites and position and so on is usually a problem of money. So science is it's a trade-off, but I didn't mention that at the moment, both for Cosmic Explorer and Einstein Telescope, there's a group dedicated to search for site and take a decision where they would put the detectors. In Europe, it's not that easy because it's populated. There is 3 sites for Einstein telescope, one in Sardinia, one in nearby Maastricht, and another one in Saxony, near Dresden.
Now that I have both microphones, Marianne will be outside at the coffee break, and we'll have a session this afternoon to discuss all this, so we can.
And we have the next part.
And we
on
have the
models,
next part.
because,
Yes,
we rely on models.
that's right.
To do that.
The less depressing part will be next. Okay, we'll reconvene at 10.